Okay, over I think 2 days, 3 days. I don't remember how many days I started doing the multi-cal section, but I think I did most of multi. I mean, I did. I'm starting the integrals now, which I'm not looking forward to because I remember a lot of pain in that section. But I still haven't done the hyperbolic. But the first thing I will say is that I finished up proving this portion where we show the connection between time with if you got rid of time with chain rule. And I put this curvature of a plane curve because I'm going to re-explain it later on in theory B, because usually I don't think I ever used it in math. I used it for theory B, and what I'm going to do is actually I'm going to put that in book two, part two, because I think I want to make this book at maximum 600, but I want less than 600, probably like 500, and then so I can add on more questions, because I'm obviously going to add on more questions that I think are interesting and increase the knowledge frame. Um, but anyway, so I showed the velocity, speed. I showed speed because we could have a magnitude this way, this way. I didn't want to deal with all that shit. So I wanted to show the speed or something, and then I said, yeah, this should do the trick. I just realized it's off center a little bit, which is fine. It's not going to be a big problem. Um, so that's the only thing. I think that's the only part I fixed from the original ones. Except for the chain rule over there, I messed up on chain rule, so I fixed that a bit up. And then we started multi-cal with the plane thing, with the orthogonality vector that defines the plane itself. I used Geo whatever and Desmos 3D Desmos calculator to show it would work. Um, I think it works. I don't really know if it resonates too much, but I show that it's orthogonal, which is the most important part, I think, um, to figure out that this plane is defined by the orthogonal vector. Yes. Anyway, we start with showing that off with a determinant, and we can figure out the orthogonal vector, which gets you the equation over here when you plug in a, b, c, and then plug in the one point over here into here to get -6, the last portion, plug back. Um, and then we continue over here where we get the two vectors to get the determinant to get the negative side to show that there's a positive negative. For some reason I remember in class only being taught the positive version, which I was like, I know why, because it's kind of obvious what happens with the other step, but I just said, I'll just intuitively show that there you can go the other way and still get the same thing. um, and then we go straight to line, which is quite amusing. As I showed it with points first. Not really that useful actually. Still haven't used this version of a line ever. I don't think, at least. Um, then we go to planes and get the angles. I have actually used this for 180, so it was kind of useful. It's for if you go to orbital mechanics, and if you want the I forgot. If they're playing like the normal plane and getting the angle of satellite, so that you can get multiple satellites in certain degrees like this. Um, so it was useful. I think I used it for 181 too. Actually, that means. And then we go to tangent lines because I said why not, and I kind of went insane with it. I said vector permanentization. Finally understood it. The thing with the vector permanentization I don't understand is why do you have to complicate it? When I was in class, they made it so that they have like plane over here, make a circle over here, make a circle over here, and a plane, another plane over here to make another circle over here, over here, over here, and that's vector parameterization. Dude, vector migration is just getting two D like x and y functions. So it was start with z, and then getting the line parameterization, the line over here. That's it. Maybe it's because they're a mathematician and I'm an engineer. I mean, I'm my major is engineer, and that class was in the math department, and maybe that's the reason why they made it so confusing. But I never understood it. Um, but visually showing it off, this is what it is, and I kind of went crazy and made a bunch of tangent lines here, just for no reason at all. And then there's a line over here that I was going to show how to get the line over here, which is kind of easy with the parameterization. This is the parameterization. Um, and then we do vector parameterization more over here. I think I did a lot of these for some reason. I don't know why, but I did a lot of those. And then we start go stage up, go to limits, and limits are just fun. um, yeah, I remember all these. This is the most confusing part to me, but now I finally understood. It's not that this is getting smaller. Um, the reason this works is that it doesn't change a function enough. What that, in my opinion, this is what I thought in my head, and it makes sense to me. When you delete the square root of x squared plus y squared to y, what you're assuming is that you have y square over here and you have x square over here, but that's basically of you can translate it into y because it's just a function. If you think about it, if x over here was a was had any number in here, number, I don't know. That's right. This is a number symbol, right? This is what I always use. If you have a number on x over here and a number on y, if you have a square root of that, it would just give you a number that's basically r, right? Basically something inside of here. That's why I finally understood what it is, but it didn't take. It took a long time for me to understand it, because what I'm basically saying is that x and y, the function of x and x squared plus y squared square root, and y has a both same frame, which means that if anything that square root of x squared plus y squared can plot out, y can do the same thing. It's just different places because x and y could be um, running in different, like when y is 3, x can be 2, but you can find it in another place that the same thing, y2 with because if 2 square plus 3 square, that's 4 plus 9, that's square root of 13. Well, square root of 13 can be found with y, and it makes perfect sense, and which is why it works. It's pretty beautiful. I love that equation. Anyway, we go to the hop, which you know, I mean, it's kind of fun. I don't know. I always love writing about hop. Um, we go beyond. We just oh yeah, we do introduce cylinder coordinates for one. Cylinder coordinates is, oh my god, just I don't know why people why the math I had in the math department they explained it one time in 20C and really in 20E, but for some reason they made it way more complicated in 20C than 20E. I don't know why. And it only showed up once in 20C, I believe. I don't remember, but this is my memory. This is my memory, which I'm trusting my memory. Oh, this is a question that I got tricked up on in class. I believe it was 20E question 3 or something. It's not exactly the same thing, but it's generally the same thing with this over here, which gives you permutation, and I just get arc length. Um, Arc length, surprisingly, I use this again in 107, so I can't actually deny it's not useful because it's gotten certain use. But the way I think about it is that there's three vectors, right? In these three orthogonal position, and you want the magnitude of it, and the magnitude of it is defined by square root of this thing, but it's still speed. In the end, is just a vector of speed, which is velocity. When you take an integral of that, you get the length, and that's how you get the arc length. It's just deleting the speed of it and getting whatever r is it. It's the magnitude of it, so it's not really the displace. I mean, it's not really the position placement, but it works well enough to get the length of it. Um, I believe it's a scalar also. Then wouldn't it? Because you're getting a magnitude of this scalar should be a scalar. That's what I believe in. Partial derivative is interesting. I was looking at this and I was like looking for like what can I add to this section because I remember this being important, but I don't remember much of it. Then I just dug up and thought of it and then remembered we did Laplace operator. So I said, you know what, I'll add the Laplace operator. You know why? Because I haven't learned it in 20C. I learned it in the engineering department. For some reason, the math department didn't teach me that. So why not add that? And I was thinking, what the hell did I what the hell the other is impartial, right? So in the end, I thought of, oh well, I can do the chain rule here, right? And I was looking at the proof. I figured out the proof is just basically, um, I hope this is the right explanation. Oh, this. Uh, it's good enough. I dragged this from 1D. Basically, I copied from 1D and then put it in here. And I assumed that the change over here didn't change, so that's the reason why it worked. I think it's correct because it makes sense to me. Probably should have double checked that before I put it in, but pretty sure it's right. I'm just gonna say it's right. I mean, I'm pretty sure it's right, right? Because I remember this. I mean, the professor, I believe, skipped the section just to show the triangle thing. But I remember researching it back then, and it was something like this, where you change it to this, and this, and that turns into this. But the middle step was gone. I think this is the middle step. I think they just want you to assume that you know about 1D thing, so they assumed that it will translate to here, which yeah, good, yeah. There's a tree diagram. I was going to add it, and I just thought to myself, do I want to add the inferior, not the inferior, the worst way to do something? I was just saying, no, nah, we're getting rid of the tree diagram. For some reason, the math department makes fun of you for doing it and also wants you to do it. Kind of weird. The math department. I remember the professor saying that this is not the actual method, but this is a good way to memorize it. At the point of time, I thought they were like going to show the proof of it, but in the end, the proof was, I believe, this, and then they skip right here, I believe, to the end. They didn't show any of the middle step. The middle step is not really that powerful because it's basically going to 1D and dragging it back here. So it makes sense that they skipped it, but I re-added back in because I added back in here because it confused me a little bit back then. Why they skipped all the way to here, which sure, fair enough. Um, anyway, oh yeah, right, this plane thing. I should probably prove this, but this works. Yeah, I should probably prove that. Good thing to do. Anyway, the next part is one part I didn't get. I used ChatGPT to get this graph, which made me understand what the hell was going on. Apparently, there's a 2D form over here that goes like this, and you're looking at how much of the velocity is this way, and you're getting you're pretty much getting the, you know how you get the partial of the, like, if you have if you have velocity vector this way, but you use cosine to get down over here. That's pretty much all it's doing, but doing it in the most convoluted, weird ass way, which actually works out. I have no idea what the use of this is, but I do know that it can be complicated hard with this shenanigans. And this shenanigans, where you have X, Y, and Z, what happens is that, from what I can observe, is that you can't really plot that in 3D, but you can actually if I do it this way, it kind of shows what it looks like. It's basically gonna, if you were able to plot in 3D, most of the time it will just give you a big box, solid box, because it goes everywhere. It's all continuous everywhere, and everything's true. Um, but by make splicing it a little bit, I was able to show what it would be in 3D space. But in reality, I'm not sure if this is a good function at all. Probably not a good function, honestly. Um, it works. I don't care. I don't really know the use of having a function in X, Y, and Z, and then another. So this is like a four variable function. Like there's the f x y and z is basically w, and there's x y and z, that thing again. So there's four variables. Not sure the use of it, but we can either way get the plane of it. You can get the what's again. This why do I have it again? um this grabs you the tangent of that when it's at this point, and then you can get the speed of that, how fast it goes, and if you point in that direction. So it's three variables, so we're moving it back to, oh, that probably was the reason why that only makes sense now. It makes sense why that happened. You're getting a plane over here, and using that plane, we are getting a speed at that any direction we go, and that makes sense. Over here we're making a 2D plane instead. That makes perfect sense. We're making a plane over here. That makes sense. So we're going back to 3D from the four variable thing and doing this speed over here. That makes perfect sense. I put the hasty matrix here because it's partial. There's a confusing partial for Taylor series, and I just said I'll put it in here. Not really useful right now. I don't really think you will need it right now. Hasty matrix is a pain in the ass, so I'll put it there for now. Now 3D. Now this I don't have a proof for. They just gave it to me and said this works. And I searched. I think I long time ago I searched. I still search for it. I think I did search for it. For proof of this, I gave up looking for it. I probably will look for one more time before I say I give up. But generally speaking, this is what it is. Getting the max and min, getting the max and min again, getting the max and min again, getting a local max and absolute max and min with the bounding straight is a little bit more confusing. We'll use Lagrangian multiplier to get this, but we'll learn over here that there's an easier way sometimes, not all the time. Sometimes you do need to do Lagrangian multiplier, which is just doing whatever this shenanigans is, where you do g of x and doing all this math, which it was okay. It was not that bad, honestly speaking. Over here is where we do the vector pyramids. This is another way to get a max and min in a boundary. So the first thing I did was get the saddle point, or was going to get it until I realized it was not valid for the bounds over here. The bounds didn't get it valid, so I put the over here that didn't work. So we used vector parameterization, because you get a line when you vector parameterize, right? You are trying to get the intersection of that. So you get a line over here, and we're using 1D movement to get the max and min. And we get the max and min from this function by getting, I believe, the zeros from the first derivative, and look at the positive and negatives, positive and negatives. There was one over here, this one, if you look over here, that I thought was useless, so I didn't want to put it in, but I had to because the question I asked for it. My question I asked for it, so I should have put it in there. So I did put it in there, but I honestly think this is a completely useless notation I put in here. Now Taylor estimation is oh yeah, we did a tangent estimation over here. Was kind of fun to play around with, but the main event is the Taylor series because it was a pain in the ass. I started off with E of x, which is, I believe, considered one of the more basic ones because I've seen it everywhere and it always shows EX plus Y, I believe. Um, well, that's the first thing anyone thinks of, anyways. And then we go over here with the Hessian matrix, and then we go with this big function and these big functions. I put this in here because I know it's pain. Also, that in reality, I just want, if I were to do something like this, I would just copy and paste this, and I would work from here instead of doing this confusing summation, weird ass summation that was trying to figure out how to make summation out of this shenanigans. Pain in the ass. And yes, that was a pain in the ass. And now I'm going to integrals over here, multiple integrals. And then I did coordinate system before that because honestly, I need to review how to do this. I forgot how to do this, so that's going to be a pain in the ass. I'm not looking forward to it. Anyway, the Jacobian matrix is one of the more important things in which function in the moment of inertia. So something I was gonna, and there's relative values, all the information I'm gonna have to unpack and put it into something. And then ODEs I haven't even really touched properly, so this is a mess and a half. If it's in a box, it's always a mess. As you can see, I'm slowly deleting the titles, like 20A, 20B. It means that it's mostly good enough for most people to look at and understand and figure out what's going on. Again, this is some of the content is you might need other material because I'm shortening it a little bit and putting I think at least most interesting and harder normal questions and the I mean, it has more explanation on proofs than anything else. But for now, but I think it's some way harder than the normal book that we have usually, or somewhere sometimes easier. Depends on what you're looking at. If you're looking at proofs, then it's much easier because I'm an engineer and not a mathematician. I'm not that like for example, I'm not into all those like givens and statements on the geometric one. um, I remember the geometric one, you had to do this kind of proof and I just didn't do it. Instead, I used just calculus to prove everything. And I believe my math proof teacher in high school said this is not considered a proof. You can't use it as a proof. But I just said, nah, it's good enough for a proof. I don't really give a crap. In my opinion, it's a good enough proof. This is a proper proof, although these are proper proofs. What I mean by that is that you need to do givens and SSS and all this shenanigans if you're interested. I don't know why I still have tables here. I thought I zeroed out everything. Um, Let me give you one example of a proper geometric proof that yeah, I use the Jacobi matrix here just to figure out this thing because I was saying I'm not doing all that proof. That makes no goddamn sense to me. Here it is. The actual geometric proof, the way you're supposed to prove everything, with the statement reasoning and all the shenanigans. And I just said I'm not doing any more of that. That was me in the past. I would have loved that in like 10th, ninth grade. I did love that because it was easy as shit back then because you pretty much copy and paste from a big ass cheat sheet that gave you every answer in there, and then you just miss and match puzzle. But I realized that after that class, it just became a pain in the ass to remember. So I'm not ever doing that ever again. That's never gonna touch my brain ever again, probably. And then oh yeah, I also restructured this. I'm gonna put more multiplication because that's the most confusing part later on. And the other thing I did, I revamped the determinant one because I realized I need more determinant questions. So I showed that there's more than one way to do a determinant, and I left the dot product like it is because it really didn't matter at that point. But I did more determinants over here and cross products over here to reinforce the cross products and determinants. And then I think we did the vector unit vector here. Yeah, just making it more what's the word clearer on what we're doing over here. Um, yeah, I think that's all the changes I have made. I don't think I made more changes, but at least now the multivariable calculus is actually readable, except for the integral part, which is a big section. I'm not saying it's not. I'm gonna do it. I'm gonna change everything and fix it, because obviously, uh, it's a very 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 important part. Um, yeah, very important. Uh, I was just looking at this and doing painful work over here. It was very painful to do this. Um, um, I don't want to touch a Taylor series for a long, 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 long time. But I will have to because I know that so far most of my classes had Taylor. The recent one, 107, had so much single variable Taylor is exaggerating. And then in the end they did two D Taylor, but it was not really that powerful because it really didn't do much of that. Then we did a little bit of Taylor in which section I believe it was something in fluid, I forget. And then a few Taylor over here and there, but mostly as a proofing mechanism, which is kind of weird. I don't know why they would do it as a proofing mechanism, but basically, if there's a small point, Taylor series. I think I'm done here. All right, there's one last part I want to show you guys. I forgot, which is all the things I did. Just to show you all the graphs, and then this one has it all the way over here. Let me save that. This one has it like this, and it kind of shows you all the graphs if you want to see that. Oh, I think I should have done translucent to make it more clean what they mean over here. Over here, this one I think. Did I show all of them off here? Okay, this one just shows you that. No, that doesn't help anything. This one, what does this show? This one shows something. This one shows all 4 points. All the math over here if you want to look at it. You can plug everything to Desmos yourself. Just copy what I did and you should be fine. Over here, I don't know why I have this one. This was finding a max and min. This one over here was for, I think, some kind of. Oh, this was fun. Let me just show you what I mean. Ooh, this is fun, isn't it? I find this one really fun. I don't know why. Uh, Let me look at this one. This is just showing a line over here. This one, what does this show? I forget. Ah, yeah. This shows all the tangent lines. I don't think I can actually change. I can actually. Can I change it? Oh, I can. I didn't know that. I didn't realize I could change everything. Oh, that's cool. Huh. I didn't realize I made this one like this. I thought I made this. Oh, actually, that makes sense. I had to do it that way, otherwise it would uh not work. I don't know which. Oh, that was the first tangent line I made. Very simple. This one is just some kind of weird shenanigans I did, and then I don't know what this homeworks are, but I did some homeworks over here for something else. Let's just delete that because it doesn't really. Oh, I think it was to make those plane things. Um, what else do I have to show you? Here's the graph of all the zeros over here and how you can do it. And then I think that's it. I think that's it. With that said, bye bye.